You've seen those videos, right? A robot moving with this incredible grace, this precision that almost seems impossible. And you have to wonder, how on earth do they do that? Well, today, we're going to pull back the curtain and uncover their secret sense, the very thing that makes it all possible.
I mean, really think about it. How can a machine handle something as fragile as an egg, or navigate super rough terrain without falling over? The answer is, well, it's surprisingly elegant. And what's wild is that it's the exact same principle you use every single day just to walk around without falling on your face.
Yep, that's the secret sauce, sensory feedback. It's not about having stronger motors or fancier gears. It's about this constant conversation the robot is having with itself. You know, just like when you're walking and you instinctively adjust your balance without even thinking about it. It's not about raw power. It's all about that smart, intelligent response.
All right, so let's dive into this secret sense. To really get it, we're going to start by comparing the robot system to something we all know pretty well, our own bodies.
It's actually amazing how similar the two systems are. Think about it. We have our senses, sight, touch, hearing. Well, a robot has sensors. We have our brain, the thing making all the decisions. For the robot, that's the controller. And our muscles, the things that actually do the moving, those are the robot's actuators. It's a really simple but super powerful analogy. Okay, so we've got the pieces of the puzzle. Sensors, a controller, and actuators. But how do they all talk to each other? How do they work together? Well, it all comes down to this really elegant, continuous process called the feedback loop.
And this is the heart of the whole operation. It's a simple, non-stop cycle. First, you sense the current state. Where are we right now? Second, you compute the error. How far are we from where we want to be? And third, you act to fix that error, to close that gap. And this isn't a one-and-done deal. We're talking hundreds, even thousands of times every single second. Sense, compute, act, over and over and over.
So step one is sense. This is where the sensors come in. You can think of them as the robot's eyes, its ears, its sense of touch. They are just constantly streaming in data, measuring everything you can imagine, its exact position, how fast it's moving, even the teeniest amount of force it's applying to something.
Okay, next up is the brain of the operation, the controller. It takes that flood of data from the sensors and does the most important job. It asks one simple, crucial question. How far off am I from my goal? The answer to that question is what we call the error. And that little piece of information is everything. It's what the controller uses to decide exactly what to do next.
And finally, we get to the muscles of the robot, the actuators. These are the actual motors and joints, the parts that do the physical work. They get their marching orders from the controller, and their only mission in life is to execute that command, to make that correction, and to shrink that error down to zero.
So that controller, that robot brain, how does it actually decide what command to send? I mean, what's the logic? Well, for most robots, the answer is a brilliant and surprisingly simple system called a PID controller. It's like the brain's operating system.
So, PID. It sounds complicated, but it's really just three different ways of looking at that error we talked about. The P for proportional is all about the present. It asks, how big is the error right now? The I for integral is about the past. It asks, have we had a small nagging error for a while that we need to fix? And D for derivative is about the future. It asks, is the error getting bigger or smaller and how fast? By blending the answers to those three questions, the controller can make a super smooth, stable, and smart correction. Okay, I know this might all sound a little abstract, like we're deep in the engineering weeds. But the truth is, you see this exact technology making a huge difference out in the real world. So let's look at a few amazing examples.
First up, humanoid robots. You know, the ones that walk on two legs. For them, feedback control isn't just nice to have, it is absolutely non-negotiable. To walk, run, or climb stairs without just falling flat on their face, their sensors are constantly measuring their balance, their tilt, their momentum, and the controller is firing off these tiny, lightning-fast adjustments to their joints to keep them upright. It's a continuous balancing act.
Or how about a drone? Ever seen one just hang there in the air, perfectly still, even when it's windy? Yep, that's feedback control. Its internal sensors are feeling every single gust of wind, and the controller is constantly telling the propellers to speed up or slow down, fighting that wind to stay perfectly level. Seriously, without that constant feedback, you would just tumble right out of the sky.
And then you've got these really high-stakes situations, like robotic surgery. Here, feedback control provides a level of precision that is literally superhuman. The system can sense the tiniest, almost imperceptible tremor in a surgeon's hand and just filter it out.
It ensures that every single movement of the instrument is perfectly steady, exactly as intended. When there's zero room for error, feedback control is what makes it possible.
Now, that PID controller we talked about is the absolute workhorse of robotics. But, the field is always pushing forward. So let's just quickly look at what's beyond the basics, some of the advanced stuff that's making robots even smarter.
So, the real world is messy and unpredictable, right? That's where things like adaptive control come in. This lets a robot adjust on the fly to new situations. Like say it picks up an object but doesn't know how heavy it is. It adapts. Then you have robust control, which is all about dealing with imperfections. What if a sensor is a little bit faulty or giving noisy data? Robust control helps the robot stay stable anyway. These are the kinds of advances that are crucial for getting robots out of clean labs and into our messy world.
And this all leads to maybe the most important application of all, safety. Especially when robots work with people. I mean, it's not just about controlling where the robot's arm goes, but how hard it pushes. This quote really says it all. Feedback ensures safe cooperation with humans by limiting applied forces during contact. That's it right there. For a robot to work next to you, it has to be able to feel when it bumps into you and immediately back off, ensuring it never causes any harm.
All right, so we've gone through the nuts and bolts, we've seen it in action. So what's the big takeaway here? What's the one thing you really need to remember about all this?
Well, it really comes down to this massive difference. On one side, you have what's called an open-loop system. Think of it as blind execution. It just follows a list of instructions and hopes for the best. If it gets knocked off course, too bad. But with feedback control, you get a closed-loop system. It's not blind anymore. It's responsive, it's intelligent, it can actually see what's happening and adjust.
And that really is the whole story. Feedback control is the backbone of intelligent motion in robots. You could even say it's what breathes life into the machine. It's this invisible magic that transforms a clunky, rigid machine into a dynamic, responsive partner that can actually work with us in our world.
And this technology is just getting better and better, faster and smarter all the time. Which leaves us with a really fascinating question to think about. As these systems get more and more aware, that line between just a pre-programmed machine and something that's truly responsive, well, it's going to start to blur. So what new possibilities do you think that's going to unlock in our world?